Hey everyone, this will be my last video about Agda. I want to show you where induction comes from. So there's a very deep relationship between induction and the folds that we've been looking at a lot. So I've got here pretty much blank file just with natural numbers imported. And I want to start by writing just a standard fold for the natural numbers. And we've done this many times before, so we'll call it fold nat, and this is going to work for any output type that you want. And of course we need an argument that we will return if we see 0, so that'll just be something of type B. And then I need something else to handle if I see a successor, and so this will take a B and return a B. And then finally we'll take a natural number and we'll return a B. Right, so this will go through and replace the 0 and successor constructors of the natural number with these two arguments. And so we can implement this ZSN. We can pattern match on n. And if the number is 0, then we're going to return z. And if the number is a successor of something, we'll return s applied to, and we're going to say we want to recursively fold the n. So we'll say fold nat zsn. And by the way, this is another one of those situations where auto doesn't do what we want. So if I just say auto here, it just fills in something of type B, which it gets by applying s to z, which isn't a particularly good thing to do. But we'll come back to that in a minute, because we'll see a situation where we can write something similar that does, where auto does work. Okay, so this is a standard fold on the natural numbers. The first thing I'm going to do, so I'm going to copy this. We're going to make another version of this. For now I'll call it fold nat 2. Fold nat with fold nat 2. I'm going to rename B. I'm going to call it capital P. Of course, Agda doesn't care. We can name things whatever we want. But I named it that to emphasize the fact that we can also, instead of just being some value, we can think of this as representing a proposition. So remember, there's this relationship between types and propositions. So I can think of a type as representing a bunch of values, or I can think of it as representing a proposition, and then values of that type correspond to proofs of the proposition. So thinking of this in terms of propositions is kind of silly, because this says, well, if you give me a proof of the proposition P and a way to turn proofs into other proofs and a natural number, then I'll give you a proof of P. But if we already had a proof of P in the first place, it's kind of useless to go through all this rigmarole just to get another proof. But the thing is that propositions, right, don't just have to be standalone things. They can actually depend on values. So in particular, I'm going to change this to say that the proposition P is now no longer just a standalone proposition, but it depends on a number. So it's a proposition about a number. So that we would write normally like P of n, or P of 5 might be the proposition that something is true about 5. Maybe 5 is even, right? So that even proposition that we made would fit this. So I need to obviously change the rest of the type, because now P needs a natural number. So the output is the easiest. I am given a natural number, and then I have to return some proposition that corresponds to a particular number, and so I just want it to correspond to that n. So this says whatever number I'm given, I want to return a proof of the proposition about that number n. Now let's think about how we need to fill in these other parts. So this P here right? This is the value I'm going to return if I see the number 0. So in that case, the number is going to be 0, and I'm supposed to return a proposition corresponding to that number. So if this is the thing I'm going to return, this had better have the type p of 0. Otherwise, Agda is going to complain and say you can't return that proof when n is 0. And what about this one? So here, this p represents the value we're going to get by recursively folding the number, and then this represents what we're going to return for the successor of that number. So what I want to say is if I make a recursive call on k, I'm going to get the proposition p of k, and then the one I want to return is p of successor of k, because the number that foldNat was called on here will be the successor of something. Okay, but I have to say what k is. So this is really, I want this to be true. I'll just specify what the k is, and then be able to apply this function no matter what. So let's try implementing this. So again, I can pattern match on n. In this case, let's see what we write. N is 0, so we're required to return something of type p0. Well, I have one of those. That's z, so that's good. That's exactly what I want to return in that case. And in this case, right, I want to return something of type p of successor of n. And I have something that could return p of successor of n as long as I can give it p of n. And I can get that by calling foldNat2 recursively. And here actually auto can do the right thing for us. The thing that auto filled in before won't actually have the right type anymore. The only way to get a p of successor of n is by recursively making a p of n and then applying s to it. So if I do auto, okay, well that's actually, there's a couple ways to do this. That kind of corresponds to a left fold, I suppose. Let's put in actually s. We do want to do s once, and then auto can fill in the rest for us. Just to be clear, that thing that auto filled in, that wasn't what I was expecting. It is a valid proof. It's just not quite the one that corresponds to the foldNat that we had above. So we'll do it this way instead. So let's think about this type a little bit more. So again, we have this proposition p that's going to be a proposition about some number n. And let's read what this says, right, using this correspondence between types and logic. So I have a p0 here, and I've got an arrow, so that corresponds to an if. So this says if p0, so if p0 is true, or if the proposition p holds for the number 0, right, then, and this is another if, so this is really like saying and. If this and this and this, then this. So if p holds for 0 and for all natural numbers k, if p holds for k, then p holds for successor of k, then for all natural numbers n, p of n. This is exactly the statement of induction on natural numbers. And in fact, anything that we wanted to prove about natural numbers, we could actually do it directly using this this function here. So I'm going to rename it from foldNat2 to indNat, because this is really induction on the natural numbers. And that's the main thing I wanted to point out today, is that induction really is just a fold with a fancier dependent type. So when you make your result type, instead of just being some type, it's a proposition that depends on the value you're folding. That is exactly what induction is. And you could do this same game with any type. Write down the fold for it and then upgrade the output type to be a proposition that depends on the value you're folding. and then change it appropriately, and what you will get is exactly induction for that type.